Hello. Welcome to yet another session on Bluesky Statistics. And this time we are going to focus on analysis of variance. But before I go to analysis of variance, I've actually opened a data set that we've used before. This data set concerns the height and weight of children under 5 years of age obtained within the demographic and health survey we obtained from their website for purposes of teaching. So I can use the data for purposes of teaching and nothing else. If we were to use this data, please note that they are from the demographic and health survey website, and they are obtained solely for purposes of teaching. So there's no other copyright apart from that. Now, if you look at the data, we've used it before, and it's used to determine whether children are growing normally or whether there may be malnourishment going on. As we know, malnourishment is measured by a number of factors. The starting point is that WHO publishes the expected weight and the expected height of children by age and sex. There are other things that so the expected weight at 0 months means that a child who is under 1 month old is expected to weigh on average 3.3 kilograms or be of length 50.5 centimeters. Normally the children are not yet standing, so they measure them using what they call the length instead of the height. We'll combine them here. And that's for boys, and for girls it's 3.2 and 49.9. Okay, and there are some standard deviations given for those population values. So let's suppose we look at a child who is 12 months old. If a boy is 12 months old, we expect them to be about 10.2 kilograms in weight or 76.1 centimeters in height. We are assuming that all children who are 12 months old already walking, so we should be having height rather than length. For girls, the corresponding figures are 9.5 and 74.3 centimeters. Those are the expected standard deviations. That means because these heights and weights are assumed to be normally distributed, if we take approximately 2 times these, 2 times the standard deviation, that will give us 2. If we subtract from here, we get about 8.2. We add 2, we get 12.2. So that would mean if we construct a 95% confidence interval, the expected weight for boys should be from about 8.2 to about 12.2 centimeters, okay, in terms of interval estimation. And for girls, we can do exactly the same thing. The standard deviation is also 1. So if we multiply by 2, we get 2. We subtract 2 from 9.5, we get 7.5. We add 2, we get 11.5. So we see that the 2 actually overlap, even though they are different. Even though one is 10.2, the other one is 9.5, the confidence interval overlap, which means if we use a hypothesis test, we cannot separate the 2. But they are not identically the same. Anyway, so we could, like we've done in the past, in the previous piece of work, evaluate whether children 12 months of age are meeting these expectations or not. And whether or not they are meeting, we can check whether the boys and the girls are growing at a similar rate, a comparable rate, whether or not they are meeting. The first question will be a 1 sample t-test. We are just focusing on whether the boys 12 months are the expected weight is 10.2 kilograms given the sample. And we can do the same for girls. We can now, okay, so that will be 1 sample test because we are focusing on 1 group of people. If we want to compare boys and girls, we are now focusing on 2 groups of people. So we have a 2 sample t-test. And in this particular course, we want to be able to extend that beyond 2 groups, multiple groups. So we are going to start by just revising our 1 sample and 2 sample tests. And then once we do the revision using this data, we now go ahead and do the analysis of variance. Okay. So in here, the data are already loaded in Bluesky. We wanted to do a 1 sample of the way I've said, which is just focusing on the boys. our data consists of boys and girls. The girls are wrongly spelled here. So let's go to the variable view and correct this. This should be female, not female. So let's go here. I can correct that from here. Okay. So this should be female. Add an I and with an E. Now note that boys' numerical value is 1 and the so save. That's corrected. So though the numerical value is 1 and 2, when this has been converted to factors, we use the actual names when we are doing selection. You could try using the labels and see what happens, but I think we use the actual names. So here we just also change this one to be capital. They're consistent, capital male and capital female. This is how you labels. Go to variable view and go to levels and your labels. Okay, let's go back now to our, well, we don't have to go to the data. We can go to the data set. Once we're inside the data set, okay, not in variables. If we're in variables, we can do the changes. When we're inside the data set, you see the menu is different. Go to variable, you see the menu is also different. Okay? You go to analysis, you see the menu is different. So we'll go to data sets. So we're taking a subset of the data sets. Now we can see a new menu which includes subset. So in here, let's take boys 12 months. Let's call it boys 12 months. And I'm only interested in taking the, what could we take? Let's take the weight in kilograms and the height in centimeters. So we have the expected values. Okay. And then here we do the subset selection. There are various ways of selecting subsets of variables. We want to use 2 variables. We want to select based on the sex and based on the age. So this is option 3, or actually option 2 is our best one. So here I'm going to say child sex is this one, CHLD underscore capital SEX equals to, double equals to, since that's a logical statement, and we are saying that is equals to may, okay, and because both conditions must hold, and the age, which is a capital AGE, must be equal to 12. Okay. That will give us the boys. Let's run and see if we have any data for that. Okay, so the data has been created. And we'll go here. That's the data for boys age 12. Okay. So we can now conduct a one sample t-test. Let's go in here and see what the limits are. So for a 12 years old, for the test for weight, we can test the one sample t-test H naught mu equals to 12.2 against H naught mu is not equals to 12.2. So let's go and do that. We come here. Now we're doing analysis, so we must go to the menu, analyze or analysis. And we are comparing means. So we just come straight and do means. And we're doing a 2 sample, so we're doing a 1 sample test where we only have 1 group of children, which is males. So we'll do a 1 sample t-test. I'll just have it there. Okay. And we are doing for weight. We can't do both because the expected values are different. Okay. So we cannot put weight and height because the expected values are different. So we are saying this should be 10.2. We want to include 95% confidence interval. Our alternative is not equal to 10.2. Usually, there's a normal expectation that the, okay, let's just test that not equal to 10.2. We can do native ones. So let's do some effects. If we want to, we can display some effects there just to see what the effect sizes are. Okay, so let's run that guy and see what it tells us. Are children in Benin, based on that sample, growing normally like other children, or they are not growing normally? So let's see what happens here. So what does it tell us? Okay, so in here, we have that the difference X bar, the sample mean for Benin, there are 89, well, 90 children anyway, because this is n-1. The degrees of freedom is n-1. We can check over there that indeed there are 90 children. The mean weight is 8.7 with a standard deviation of 1.53. And then when you take this standard deviation divided by the square root of the sample size, the square root of 90, you get this number here. The standard error is the standard deviation divided by square root of the sample size. I check that manually, and you get that. Okay, and we'll now do to the test. It's a t-test because we didn't specify the standard deviation. Actually, Bluesky does not give us the option to specify the standard deviation. Maybe it's something worth communicating with them and see if they may be interested. So in here, the p value is less than 0.001. Now, what is the p-value again? The p-value in a very layman term is a probability that the null hypothesis is true. What's our null hypothesis? Our null hypothesis is that the mean, the population mean, is 10.2 kilograms. And our p-value is very small, which means the probability that the mean for Benin children is 10.2 is the probability that is 10.2 is very small. So we reject that null hypothesis. We conclude that the mean weight for 12-year-old children in Benin is not 10.2. We already see that it's 8.7. That means that the children are actually underweight compared to what the normal weight should be. Okay? You can see the confidence interval, 95% confidence interval indeed does not include 10.2. Okay, it's lower than 10, the upper limit is lower than 10.2. So we reject the null hypothesis and we conclude that indeed the expected weight of children in Benin 12 months, boys in Benin 12 months old is between 8.4 and 9.1 with a 95% confidence interval. Okay. The effect size, you see, is negative, of course, and it's quite close to 1. That's a very high effect size. If there was no effect at all, this effect size should be 0. But in a value far from 0, it means that it's a high effect size. Okay, so that is done. The boys, we also do for the girls. So I will do for the girls, even though if we're in class, I would want you to try it yourself and see that you can repeat the same for the girls. But since it's a recording, I will do it, but I want you to go and try it yourself. So I'll just go back here. And that's data selection. Okay, and now I want girls now instead of boys, so I'll just check this to girls. G-I-I-R-L, girls 12 months. And in here, the only thing I need to change is to change from male to female. Female. So I'm changing from sex equals to male to sex equals to female. So we said I'm keeping everything the same. I'm creating the girls data set, and that is it. So I can run that data set. And I hope this is good practice for you. I always like to add a few things to the lesson so that you don't just, you gain more skills. Each time you go and do something, you gain more skills. So let's see, I run that. And we now have the data for girls. It's right there. The data for boys, the data for girls. So we can go now analyze for girls as well. First, let's check what the expected values are. The expected value is for girls is 9.5. So let's go and do that check. The new data set, so we'll have to start with analysis again. Mean is again one sample t-test, and we're looking for weight. We are saying that the weight is 9.5. We can also still include the effect size. Anything else, I think that's fine. Let me just make sure that's 9.5. 12 months or 9.5 exactly. So we can run. What do we find? So our null hypothesis there, H naught mu is equals to 9.5. It's a one sample t-test. What do we find? There are 104 girls, 12 months of age in this sample, and their mean weight is 8.2. The standard deviation of 1 point that. Standard error again is 1 point, is the standard deviation divided by the square root of n. So it's 1.034 divided by the square root of 104. That should give you points. They say that actually, that comparison, the mean, the standard deviation for girls is actually smaller than what we found for boys. The boys were of 0.5 this. So the values for girls are more precise. Girls tend to be more similar to each other than the boys, or the ages for boys is more variable. Okay. And confidence interval says it's from 8.07 to 8.07 to 8.4. So that's what I mean. So the confidence interval is much narrower. So girls are really, most of the girls are very similar in height. From just between 95% confidence interval is 0.81 to 0.85 approximately. If you compare to boys, the boys were much wider. It was from 0.84 to 9.1. Okay? And if you compare just this confidence interval, the lower limit for boys is 8.4. Let's look at the upper limit for girls. It's 8.47. So they barely overlap. There's an overlap, of course, but barely. So 8.47. So girls seem, even without doing any format comparison, girls seem to be shorter than boys. Because of this overlap, if you do a test, we may not dictate the difference. The value may be close to 0.05. But anyway, we're going to do that just now. So that's our one sample t-test. Of course, we know the assumptions of one sample t-test is that the children were selected independently of each other. So all the children were independently selected. 104 children were selected independently. So that would mean that we are not really necessarily expecting 2 children from the same household, although that's not really a big deal. Okay. Now, let's go now and say, okay, we want to do a 2-sample t-test. So we'll go back to our data. So instead of selecting boys and then girls, let's say we want to select boys and girls. Okay. So I'll just say children, the child is 12 months old. And in that case now, I'm no longer putting any condition for sex. So I'm selecting all children who are 12 months old. Okay. So I'm selecting only children who are 12 months old. The child is 12 months old. And then I can select the data. Now let's include the sex of the child, because we want to see sex of the child. We could include one other variable. My mind is saying that why don't we include one of these? Well, okay, let's leave it. Yeah, let's include one of these variables. Let's take this one. Yeah, let's take the distance. Yeah, it's nice statistics, so let's take it. We even take the month of the month of birth, but now let's leave it that way. Or even the sex of the head of the household. Why not? So, but for now, let's leave it like that. So that is the source I'm selecting. These are the only variable I want to include in the data set, and I run that. Okay. So the data has been selected. It's there. The weight, the height, sex, the statistic. So now our interest is to compare male and female children. And we can use any of those two. When we compare male and female now, we are not interested in the population values anymore. We are only interested in where male children have the same weight as female children. Male children have the same height as female children. That's a 2-sample test. And please note the difference. When we did the 1-sample test, we came here, the 1-sample test, and we say, are these children, is the weight of these children consistent with children who come from a population with a mean weight of 9.5 kilograms? We assume that the weights are normally distributed. That's a very important assumption under this test. We assume that the weights are normally distributed, and we're saying if the weights are indeed normally distributed, are these children consistent with children from a population where the mean weight is 9.5 kilograms? Now, what we are now trying to do is compare males and females. So again, as we've done before, go to analysis. That's a 2-sample test. What do we mean by 2-sample test? We mean that the boys were selected independently of the girls. That's what 2-sample means. The boys the 104 girls were selected independently of the 90 boys. Not there are 90 boys and 104 girls. In fact, we can just check that. We can go to summary, frequency, and then tell us the distribution. Actually, let's just do the two of them. Let's see how many children are in each group. But we already knew that it should be 90, 104. As we see, male there were 90, female there were 104. What about the D-stat? Where's our D-stat? D-stat is 144, 50. There are no missing values in that case. So what we are testing is that is a mean for male children in Benin, the mean height or mean weight, the same as the mean weight or height for females, given this sample of 90 random selected boys 12 months old, 104 randomly selected girls 12 months old. They have the same mean values. Okay? We don't expect them to be the same based on the WHO value, but let's check to see if they have the same. We come in there and we'll do analyze now independent sample. Dependent sample. Now our variable is the weight. Now we see that we are now taking the sex of the child. Okay. And it has to have 2 levels only. If it has more than 2 levels, it will not work. And then we are saying, are the means the same? Are the boys and girls having the same mean? Okay. We can also look at the effect size. Now, the effect size should be 0 if the male and if the boys and girls are having the same. If it's different from 0, it will tell us that there are significant differences. Let's go and see. Just one thing, we could actually put all the variables in there. So if you remember, okay, now let's finish this first. So what do we have here? As we said before, we already have the statistics. The mean, the sample mean for males is 8.73. The sample mean for females is 8.27. The standard deviation, is 1 point this. Let's see if something has happened that I was not expecting. Something has happened. Something has happened. This is 1 point this and this. The standard deviations. Let's check. These are the standard deviation I think we had before. Standard error now that I'm checking. I think this standard error are not based on that sample size of 90. This looks like the pool standard error. It's a bit curious. Okay. Yeah, no, this is the old model that I think I've not updated my model. Remember that when we did the when we did this analysis, we found that this minus this is 0.06. So this is the old model. I've not adjusted it. Okay. Yeah, okay, we're going to adjust it. Your own may show the same, but there's been correction. Remember, there was an error in class we noted, and Bluesky for correction. They have sent me a patch, which is not yet corrected here. So these are not exactly the correct values. But anyway, the test itself is fine. So our test is showing that we reject the null hypothesis that male and females, boys and the girls 12 months will have the same weight and the same weight. Okay, that's the p-value for the H0, and H0 state means are equal. Now, if we look at the difference in mean, that's the difference in mean here, and it doesn't include 0. So since the difference does not include 0, it means that, and it is positive, means the mean for group 1, which I think should be female, sorry, it's male minus the mean for group 2 is female. So that is the difference in mean. The difference in mean is significant. Okay? That's the difference in mean is 0.456 kilograms. So males are on average 0.456 kilograms heavier than girls. If we convert to grams, means that the male children are 456 grams on average heavier than the girls. The confidence interval is from about 90 grams to 822 grams. It's very wide. It's almost a kg, and this is just 90 grams. Okay. Equality of variances is actually rejected. And when it's rejected, it's saying that the variance for males is different from the variance for females. That's the Levin's test. When that happens, this is the more reliable confidence interval. Okay, this is the wrong statistics. I'll go and update and check. Okay, so that's our two sample t-test. We'll update the Bluesky to get the correct standard error of the difference. Those are the tests here. So what is the conclusion? Here we know we have concluded that the males are heavier than the females, or more correctly, the null hypothesis that males and females have the same weight is rejected. Okay, male and female 12 months old do not have the same weight. You could repeat that at 0 month. I will let you do that. We'll repeat that at 0 month and see what happens. So take the sample size at any other month and then compare males and females. Okay. The sample size in any other month and then compare males and females. Now, what about the purpose of today's lecture? The purpose of today's lecture is what we call analysis of variance. So in analysis of variance, instead of comparing two means, we compare several means, compare more than one mean. Okay, so I will do that by, let's generate another subset of this data which has more than one group that we could compare. Okay, so I'll go back to data sets and I'll go to, let me do it from up here so I don't need to do everything again. So I'll go to subsetting of data. Now here, let's suppose we select children by certain month. Okay, let's select children by certain month. We just do boys, for example. So we just want to do boys, we can go to where we actually selected data for boys. This is female. Oh, let's do female. We are here in female, so why not? So let's select female children. These are girls. I want to select them by certain months. So let's say children were born in January. Let's compare them with children were born in June, and maybe children were born in just random numbers, 4 random numbers. Or we can just even take them and then just include a month. Yeah, let's just include a month. So we'll keep the same data set. No, I think so let's take month of birth, add it there. So let's add the month of birth. We're going to convert it to a factor anyway. At the moment, it's not a factor, so we can't really use it. Convert it to a factor. Just to keep it there. So this is going to be a lot of months. So why don't I do now let's put some bracket, either birth month. Okay, do like this, and birth month less than, I'll just do 3 months, the first 3 months. That birth month less than 4. Or less than 5. Birth month less than 5. So these are girls born between January and April. And I'm just going to override that data set. Let's override it. These are very override. Okay, that's it. So this is our guess, and we do the birth month, and we say the birth month should be less than 4. So we can go to analysis and do summary to see whether indeed we have birth month less than equals to 4, should be less than 5, so it should be 1 to 4. So we have 38 children born in January, 11 children born in February, 8 girls born in March, and 5 girls born in 5 girls born in April. The number is dropping so significantly. This rather small number for doing a test, but anyway, we'll go ahead and do the test for the same. If we try to now do our analysis of variance, our analysis of variance, we're doing a one-way analysis of variance. Okay. We're not doing repeated measures, it's just a straightforward one-way analysis of variance. So we'll do one way with blocks, one blocks. 1 and 2 way. So let's see this one. Okay. So this 1 and 2 way. So we're doing one way analysis of variance. That's quite interesting. So if we try to put this here, see, it doesn't accept it because in a one-way analysis of variance, the grouping variable, just like in t-test, in two-sample t-test, the grouping variable must be a factor. So we can't do this analysis until we transform our data. So let's come here and convert this data to a factor, which means to change the variable must go to variables, and then say we want to convert the factor. What we are converting this one. Okay. So convert to a factor. Okay. Now you can say as a factor. You can even actually go and name them now. So we know that these factors here are, so we'll put them here. So this is January, comma, February, comma, March, April. I need to put that in post. Let's see. That's oh, okay, this is January. I do know. Oh, sorry. This is January. So we used to SPSS this February. This is March. And this is April. This one is delete. I'm not sure I will be in the different videos. So we've just labeled them. Now we can go back to where we wanted analysis. Compare means one way and two way. We're not doing blocks or anything like that. So we have let's compare the weights again, and then we are now doing by month. Are there any options? No interaction terms. We don't even have interaction terms because we have only one factor anyway. Post hoc Levin's test of homogeneity are important. Pairwise comparison, that is also important. We'll come and see why we are doing pairwise comparison. Well, for now, I will leave it for now. Okay, I'll leave that for now. I'll just do Levin's test Because our test must assume normality, where some must assume constant variance. If not, then we must interpret the result with caution. What you have in here, so let's do okay. Oh, the results are okay. These are the estimates. Oh, the results are okay. So to be right to the bottom, I was wondering what's going on here. So there's the analysis box. And here, what we have, January, we knew there were 38 girls. And for those 38 girls, the mean was 8.3. For the in January, February, the mean was another 8.3. For March, it was 8.2. For April, was 8.5. So they said there's really no consistent pattern. They also give us the medians values, the minimum and the maximum. Minimum is from 6, the range from 6.6 to 10, 6.7 to 10, 7 to 14, 7.8 to 10. So they said the ranges are overlapping. What about the standard errors? These are standard deviation. Remember, variance is standard deviation squared. So this number here, 9.946 is 0.973 squared. Yes, so these are standard deviations. So based on these values here, don't expect to see any result telling that the weight differs by month. They're just based on what we are seeing. But does the statistics test confirm that or give us something contradictory? Here we have degrees of freedom is 3. Degrees of freedom is number of groups minus 1. Since we have 4 months, 4 groups, 4 minus 1 is 3. These are what we call the sum of squares due to month. That can be explained by month. This is the sum of squares that can be explained by residual. That means if we take away the effect of month, whatever that is, then we have 61. The amount of variance unexplained is 61 points. So the total variance in our weight data is 61.525 plus 0.266. So basically, almost all the variation is explained by the error. Very little of the variation is explained by the month, which is no surprising. The f-size is almost 0. The p-value is almost 1. The p-value against the null hypothesis that all the means are equal. The mean weight is equal for the children born in January, to the children born in February, to the children born in March, to the children born in April. And our p-value for that hypothesis is 0.9. This is almost perfect. So we have very, very strong evidence in support of each not that the weight of the children do not depend on the month in which they were born. Okay. So the weight of the children does not depend on the month on which they were born. What is here? This estimated mean, this means adjusted for any effect of month. Okay. So they're adjusted for any effects of month, and that's what we get. What are we doing? So this Levin's test. Levin's test for equality of variances. Levin's test said the variances are equal. The variation in ages for the different months are all equal. And again, the null hypothesis, the p-value is very large, which means there's absolutely no evidence to suggest that the variability in ages differ from month. Okay. And our degrees of freedom, remember that total degrees of freedom is always n minus 1. So if we take 3 plus 58, we get 61. That means our total sample size is supposed to be 60. Okay. The number of boys, the number of children, the total number of children for the 4 months is 62. Well, that is what it's telling us. The number is 62. Should be shown somewhere. I'm trying to see where that number is shown. You see where the total is shown. I can't see it, but it will be 62. If you add them up, you get 62. Okay, so there's an example of, and you can see the effect size. The effect size is measured by ether when you have analysis of variance. So you can see that the eta is almost 0. Okay. Eta is almost 0. The confidence interval in fact includes 0. We could do something that we know will lead to differences. Okay, so let's go back to that data. Let's go to the data and do something that we know should produce differences. So I want to take different data set now, subset. Let's come in here and say we're not really interested in birth month. Okay. Let's look at the age of the children. Okay. And what I want us to do, take instead of age equals to this, I want us to take age equals to 6 months. Okay, 6 months. We'll take, and you can take your own sample. Age equals to 12 months. Okay, and age equals to 18 months. And age equals to 24 months. Okay. One more, and age is 6 months. And I'll call that guess 6, 12, 14, 24, 6, 12, 14, 24, I'll do 0, 6, okay. 0, 6, 12, 14, 24, 6. Okay. You can name anything you want. So that's what I'm going to use. So I'm generating that subset of data. Age is 6. No, this will not be an. There's nobody in that age. If I do okay, there will be no data generated. Just to show you that no data will be generated. Let's see. Okay, there's no child, there's nobody there. Okay. Or there's equal sign, which is wrong anyway. So let's go back. Data set. We are taking from here. And let me go back to that command there. Yeah. Yeah, I think I made a mistake here anyway. You can't put equals to. It has to be the logical equals to, which is there. Let me go to the N and C. That's also wrong. It has to be logical equals to. That's why we're complaining. But the point is, as I said, no data is going to be generated here. You can try that because there are no children who are age 12 months and age 14 months. Okay? There are no such children. So if I try to run this, tell me that the data set is empty. Okay? The data set is empty. We know that. So what do? We use the OR. The OR, which is here. That's the symbol for OR. I don't know if you type in word word, but that's a symbol for OR. It's just that line. Just copy it and that means OR, and that means OR, and that means OR, that means OR. Okay. So now things should be good. Okay. So the data set has been generated, is there. The data is there. Just check to see that indeed that's what we generated. Let me do frequency analysis, go to analysis, and go to summary frequencies, and we're going to take just the age and see that we have 5 age groups. 6 months, there are 257 of them. 12 months, 194. and so on. In 6 months, 187. So the sample sizes are fairly high. I think I selected all the children, or were they girls? Age, yeah, I think we selected all the children, both boys and girls. No, it doesn't really matter. It's a random sample. There may be other group structures in the data. So now let's go and test to see both height and weight. If we compare them, what does it tell us? So if I go to mean, again, I'm looking at the one-way, one and two-way. We're not looking at random blocks or this, so we're sticking to just this one. Okay, one and two-way analysis. That's the option we have in here. And once again, we're comparing the weights. Now we know again, we put this again to say no because it's not yet factor. So we know we have this expectation. So we go back and say, sorry, let's make it into a factor first. Okay. So we take the age, go to variables, convert to factor, and we're converting age to a factor now. So I can use an analysis of variance. Okay. Now we do okay. So I do the conversion. Now we say it's converted to a factor. Now that is a factor, we can then go back to analysis, means, one and two-way analysis. We are taking the weight and we're comparing the weight at different ages. Okay. So what is our expectation? If we're in class, you answer that question. Since we're not in class, we'll answer it and go. We know that children at this age are continually growing. So we expect the weight of the children to be continually increasing. And we expect to reject the no hypothesis. We also expect that children who are further apart in ages should have greater differences. And this is normally tested in standard analysis of variance in what you call the linear by linear association. I haven't checked whether that's done here, but anyway, the point here is that we expect older children to have significantly larger weights than younger children. That's what we expect, but there's no way of testing that directional test in analysis of variance. Look at here, there's no way of saying the direction. So in analysis of variance, we cannot test one way or two, so we cannot test one-sided as we did in two sample and one sample t-test. So that's where it's immediate difference. Though I'm expecting that older children should weigh more than younger children, I can't test that hypothesis. I can only test that children don't have the same age. Okay, so this is a generalization that not equals to. Again, we should always do Levin's test, and we'll come back to this menu, but let's just see what the outcome gives us. I'll clear this so that I can start with the new menu. Okay, so I'm clearing that. Fortunately, I've cleared, but anyway, it's fine. So go in here, and that's our analysis. So we can go to the top of the analysis. That's what we get. So 6 months old children, the mean weight is 7.22 kilograms. 12 months, the mean weight is 8.4. This 14 months is 8.9. 24 months is 10.5. And 26 months is 11 point this. So we can indeed see the increasing pattern in the mean weights, from the minimum of 7.2 to the maximum of 11 point this. Okay, so we can really see the differences in those means. We can see the range of values. So for children who are 6 months in this sample, the 257 children 6 months, the weights range from 3.4 to 14.5. That's quite a big range. That's the standard deviation. For children who are 12 months old, it's 8.49, and it ranges from 4.2 to this. So there's a big overlap in all the weights. Okay? Some children who are 26 months are still 7 kgs weight, whereas some children who are 6 months already at 14 kg in weight. And that brings up the question, when we say the means are different, what are we really talking about? Of a 26-month-old child, that's over 2 years, is still weighing 7 kg, whereas a 6-month-old child is already maximum at 14 kg. And in fact, when you look at the higher ages, the highest weights, the 26 years is only still 16.7, whereas some 6 years are already at that. And what is even more surprising, in our sample, there's some children 14 months who are already at 18.6. Yeah, who are already at 18.6. Meanwhile, for this sample of children who are 24 months, that's 2 years, the highest of them is still this. But remember, this sample data, this is not population data. Anyway, so our descriptive statistics is showing us quite a bit of overlap, but as group, are the differences significant? Okay, the difference is significant. This well, these are adjusted means. After you correct for the effect of age, this is what the adjusted means should be. Let's see now here where our tests are. So remember, we have 5 groups of children. So the degrees of freedom is 5 minus 1, which is 4. It's suggesting here, and then the residual degree of freedom. Why is it testing here? Oh, this Levin's test, so forget about this one. So Levin's test is saying that the variance are significantly different from this. That creates a small problem because it means that our test is not as powerful as we'd like it to be. So our test is most powerful when the variances are the same. That's a fundamental assumption. While that this one, the contrasts are now shown here. So even though we didn't ask for it, this one shows the contrast of each age minus the other one. So 6 minus 12, 6 minus 14, 6 minus 24, 6 minus 26. These are all the differences or contrast. Each of them has its own standard error. The degrees of freedom in this one will be n minus 2. Is it n minus 2 or n minus 3? So it should be n minus 5. And these are the T ratios. So it's showing us, surprise, that all of the differences are significant. All the differences are significant. So if I compare 6 months with 12 months, I'm getting a mean difference of 1.2. That means 6 months old are on average 1.265 kilograms lighter than 12 months old children. Because the standard error is very small, that difference is highly significant. Okay? Although the difference is only 1.23 kilograms, the standard error is very small, and therefore that difference is highly significant. Okay. Similarly, 6 minus days. Now, because these are all highly significant, a measure that will tell us just how different they are is the T ratio, since they all have the same degrees of freedom. So the larger the T ratio, the bigger the actual difference. Okay? So we come in here, where's the largest T ratio? The largest T ratio is here, which is 12 minus 26. What is even interesting is that 6 minus 26, oh, that's the largest actually. So that's the largest difference, 6 minus 26, which is what we expect anyway. 6 minus 24 is the next largest, and so on. So the farther apart they are, the greater the difference. What's our conclusion? Our conclusion is that indeed the weight of the children differs by their age, which is what we expect. Okay, we're just testing it to know what we expect. How much is the difference? The older the children, the larger the difference in their weight. Again, what we expected. There's nothing new. But what is the overall effect? Here, this is our effect size. This is overall effect size, which is compiling all the effects, which is moderate. Okay. The high level of effect size is the highest possible value, which is 1. Okay. So that's basically our nicer variance, one way nicer variance. In this case, our sample sizes within groups were different. Okay. And we already constructed a test which we know we are going to have differences. So it was easy for us to interpret. Now, one thing that we do in the nicer variance is to look at, let's see what Bluesky gives us as options, which normally have some further analysis when we do analysis of variance. So we'll come here and see what options there are. We already did Levin's test. Pairwise comparisons is already done. That is what they showed us there. Okay. Method of adjustment. Now, I think this is mentioned in some of the lecture notes on how do we adjust. The Bonferroni is the easiest of the methods. What it does is that it adjusts our test for multiple comparison effect. The idea is what if I take the same sample, take a sample, repeated sample, say 100 samples from the same population. I want to test the hypothesis that the mean is, let's just take one sample t test, for example. So I want to test the hypothesis that the mean is 9.5. And in fact, the mean is 9.5. So I take the population where the mean is 9.5, and I take 100 samples. Our confidence interval, 95% confidence interval stays 95 of those samples, I will accept the null hypothesis, and 5% I will not accept the null hypothesis. Okay. That is what that test tells us. So by issue of just by taking different random samples, some will be more extreme, and we expect about 5% of them, if data are normally distributed, to be more extreme. The less normally distributed the data, the more samples will be failed the test. So if I were just doing multiple comparison based on 5%, then I would expect to have a certain number of those tests saying that there's a difference when in fact there's no difference. So what Bonferroni tried to do is that take the number of tests. I want to do like in here, you can count them. We had 5 combinations, which should be 10 tests. You can count to see that there are 10 tests here. 5 combination 2, 5 groups, 2 at a time. 5 combination 2 is 10. So we've done 10 tests here. So Bonferroni said, look, let's divide our level of significance by 10. Okay, and then use that to construct confidence intervals. So that's what we can do here. It's the simplest one. There are other adjustments to that, but that will be the simplest one. And it says here, compare means compact mean. That's an interesting one. Enter the value for alpha. Okay, so let's do that. Surface test and so on. These are alternative. Turkey is another one. So on that. They're all useful. Now, most important are those diagnostics. What are we diagnostics? Our primary assumption is that the variances are equal. So we want to check if indeed our assumption is correct. We also want to see a graphical display of our data. I say plot or comparison. That's interesting. That's interesting. Effect size that is due was partial eta squared rather than eta squared. That's no problem. But the effect size confidence interval, if you wanted it, least squares means interaction, but we don't have interaction here. We have the two-way analysis of variance, and that is important, but we don't have a two-way analysis of variance. We have one way. So let's see what we have. Usually what we have is a mean plot. We say plot all comparisons. We'll try to see what that looks like. Okay. No interaction, they are not applicable, so that's fine. So let's do okay. So these plots are meant under our null hypothesis, the variability in residuals should be constant. So we shouldn't see any of these residuals being more varied than any other ones. And just even though this is suggesting that the variability is very similar. Okay? So this is very similar. Okay. This is to test for normality. Remember QQ plot we did before to test for normality. And what we find is that in the middle, the data can be highly normal, but the tails, the normality assumption is violated. Okay. The middle here is very normal. In the tails, the data are not really normal. That's quite interesting. But this one, what are this one? Yeah. Leverage test again. There's nothing particular. Okay, there's some values here that may be highly influential. This one here, that is 623. Number 623 looks like it's been quite unusual. Number 738 also looks unusual. You can go and check to see what is happening there. Number 913. It's not that far off, but and 738. Same here, 738. Something is happening there. But in here, these values here suggest that we need to pay attention to them. That the same value we've seen down there. 913, 738, and 623. So they are outliers in our data set. Maybe we should consider excluding them. What is this one? These are those. Oh, okay. This is what Bluesky does. I've not done Oneway in Bluesky before, but that's quite interesting. So these are all the pairwise comparison, and these are basically our confidence intervals. So when the confidence interval overlap, it tells that those two are not are the same, but these are pairwise anyway. So we can see where everything is lying. Here we take this. So 6 months here, of course, is that lower than, actually everything here is negative because we are taking the younger age group minus the older age group. So you can see a line of 0 here. So all the effects sizes are negative. These are the confidence interval. They are fairly the same level because they have standardized the confidence interval. Yeah, there's normally a profile plot. I can't see profile plot in here, which is interesting. Normally, I would like to see a profile plot, but I can't see that in here. Yeah, so that does it for our topic on analysis of variance. I want you to go and practice this with the same data set, take different sources of data, and see what you get. Or yeah, see what you get. Otherwise, yeah, we'll do anything else we can do in class. I hope you enjoyed the video and that it's meaningful to you, and now you understand what to do in terms of analysis of variance. Yeah. Stop recording.